the world's fastest train, explained. Inside the SC Maglev train, magnetically levitated trains, also called maglev trains, are no longer just science fiction. Around the world, they're becoming increasingly common, offering smooth rides and incredible speeds. But one particular train stands out from the rest: the SC Maglev, developed by the Central Japan Railway Company. This train is not just fast, it's the fastest train in the world, reaching speeds of over 600 kilometers per hour, or about 375 miles per hour. That's faster than a commercial airplane during takeoff. The key to this amazing achievement lies in its superconducting magnets, which is why it's called the SC magnet. Unlike normal magnets, superconducting magnets, once charged with an exciting current, can generate a powerful magnetic field forever with zero energy loss. This is thanks to superconductivity, a mind-blowing property of certain materials when cooled to extremely low temperatures. So, how does this train work? To run a maglev train successfully, three things must happen: propulsion, levitation, and guidance. Let's break it down step by step, starting with the heart of the train, the superconducting magnets. Superconducting magnets, ordinary electromagnets, face a major problem. They heat up when current flows through them, which limits how powerful they can be. But superconducting magnets are different. When cooled below their critical temperature, they allow huge amounts of current to flow with zero resistance. That means no wasted energy. The SC Maglev's magnets carry an enormous current up to 700 kiloamperes. That's almost 10,000 times more than the current flowing in typical household wires. To keep them superconducting, engineers use liquid helium cooling systems, keeping the magnets at about 4.5 Kelvin, which is nearly minus 269 degrees Celsius. For context, that's colder than outer space. Special radiation shields and vacuum chambers prevent outside heat from disturbing the magnets. Even then, the cooling system requires constant power, making it one of the train's most complex engineering challenges. But the payoff is worth it. These superconducting magnets are among the most powerful and efficient electromagnets in existence. Propulsion. Now that we have powerful magnets, how does the train actually move forward? That's where propelling coils come in. These are ordinary electromagnets installed along the guideway. By switching their polarity in sequence, they create a magnetic push and pull effect that propels the superconducting magnets on the train forward. By simply adjusting the frequency of these polarity changes, engineers can control the train's speed. This system allows the train to accelerate smoothly until it reaches incredible top speeds. Levitation. But here's the really fascinating part: levitation. You might think levitating a massive train requires constant energy input. But not with the SC Maglev. The train uses clever figure-eight-shaped coils in the guideway. When the superconducting magnets pass slightly off-center above these coils, they induce currents. These induced currents create a repelling force strong enough to lift the train nearly 4 inches off the track. The faster the train moves, the stronger the levitation force becomes. That's why, at very low speeds, the train relies on small retractable tires. Once it reaches a critical speed, the electromagnetic lift takes over, and the tires fold away, allowing for frictionless travel. Guidance. Finally, the train needs guidance, or lateral stability. How do engineers ensure the train stays perfectly centered and doesn't crash into the sides of the track? Once again, the figure-8 coils come to the rescue. If the train shifts slightly to one side, the imbalance in magnetic flux induces corrective currents in the coils. These currents create a restoring force that nudges the train back to the center automatically. It's a simple but brilliant self-correcting mechanism that keeps the train stable at all times. Power and safety. With such advanced technology, the SC Maglev requires a lot of power, not just for propulsion, but for cooling the superconductors and running onboard systems. To achieve this, engineers use inductive power transfer, where electricity is transmitted wirelessly from coils on the ground to coils on the train, with no physical contact. And what about passenger safety? After all, those superconducting magnets produce extremely strong magnetic fields. To protect passengers, engineers installed magnetic shielding in the train cars and at boarding areas, ensuring the magnetic strength always stays within international safety guidelines. The future of SC Maglev. The SC Maglev project began testing in Japan back in 1997 on the Yamanashi Maglev test line. For over a decade, tests ran every single day without fail, achieving a world record speed of 603 kilometers per hour. Thanks to its success, Japan is now building the world's first full-scale SC Maglev line, set to connect Tokyo and Nagoya by 2027. Eventually, the same technology could even connect New York City to Washington, D.C., in just 1 hour by the year 2030. This technology is revolutionary not only because of its speed, but also because it's based on the amazing physics of superconductivity. So, the next time you hear about maglev trains, remember the SC Maglev isn't just another train. It's a glimpse into the future of high-speed travel.